Hello, everyone, and welcome to Goucher Environmental Dialogues. I am Dr. Jen DeRosa, the director of our master's degree in Environmental Sustainability and Management here at Goucher College. The Goucher Environmental Dialogues is a web-based speaker series, and we feature cultivated conversations with environmental leaders, sustainability leaders, and, like today, climate leaders, and visionaries and innovators in this field. And this series is hosted, as I mentioned, by our progressive new master's degree in environmental sustainability and management. And if you have any questions about our master's degree and want to learn more about it, I'm hosting an information session about our new master's degree on November 8th at 1 p.m. Eastern Time. And I will include a link in the chat if anyone is interested in accessing any of our resources, such as the registration to future events, our webpage, and any of our past recordings of our Goucher Environmental Dialogues. You can see those on YouTube. Our conversation today is about predicting climate change. Climate change is a topic near and dear to my heart, as many people who know me well understand. And our guest is a climate modeling expert, Dr. Dan Barrie. Dr. Dan Barrie is a program manager for the Climate Program Office at the National Oceanic and Atmospheric Administration, or NOAA, where he manages a climate modeling program as well as a program that supports the National Climate Assessment, or NCA. He served on the Federal Steering Committee for NCA number 4, which was released in 2017 and 2018, and he will serve in the same role for NCA number 5. He was part of a team that won the 2019 Department of Commerce Silver Award for the assessment. Dan's background is in physics and atmospheric and oceanic science, and his interests are in drought and hydroclimate energy systems. I'm saying that wrong. Drought and hydroclimate, energy systems, climate interactions, climate model development and analysis, and variability and change in marine ecosystems. So please join me, and just a note that this is on Teams, it's a webinar, so you can't turn your mics on and you can't turn your video on, but you can use the chat to join me in giving a warm welcome to Dr. Dan Barrie. And you can also indicate in the chat where you're logging in from, because we often have people logging in from all over the place, many different states and cities also around the world. So if you're here in Baltimore, or if you're logging in from another location overseas, please share where you're logging in from. And also in the chat, if you have any questions during our conversation today, you can ask them in the chat, and I will try to give voice to them either towards the middle or the end of my conversation with Dr. Barrie. So to start, Dan, can you tell us more about the Climate Program Office at NOAA, for which you are the program manager?
Yeah, sure. Thanks a lot, Jen, for the invite to speak to the Goucher community and other folks, and the stew of terms that you used to describe my expertise and interests was great. I'm also excited. I see in the attendee list that it seems there's some colleagues from Environment and Climate Change Canada who joined the call, which is unexpected. But as a Canada file and a person who visited ECCC a few months ago, it's exciting to see those names on the call unexpectedly as well. So yeah, I'm at the National Oceanic and Atmospheric Administration, and I thought maybe before diving into what my smaller office at NOAA does, I could talk a little bit just about NOAA as a broader entity, because it's a really interesting agency. It's also a complicated agency, like I think every agency in the federal government. There's kind of a funny discussion we often have with colleagues in other agencies. We just have a really hard time sometimes understanding the structure of each other's agencies. I think the structure of NOAA makes sense to me, but when I talk to folks from EPA or NASA, they cannot understand why I'm located where I am in my agency. So hopefully I could help demystify that a little bit. One of the things, and I'm a huge fan of NOAA. I'm a big NOAA booster. I love our mission and our history. And I think one thing I would start with is just a little bit of the history of the agency. NOAA formally was created in the early 1970s, but it was an amalgamation of a number of government agencies that had existed for a long time. One of the oldest parts of NOAA is the Office of the Coast Survey, which is actually the oldest scientific agency in the federal government. It was created by Thomas Jefferson, in fact, during his second term in office in 1807. And as you could tell from the title, at that time, having a good understanding of our coastlines and the depth of water in different ports and areas that are commonly sailed along our coastlines was very, very critical early on in the post-independence history of the country for both military but also trade purposes. And so it's not surprising that that was a function the government took on very early, was to map the coastline and help ships navigate our coastal systems very safely. So that's a very old component of the agency, which still has an office today. It still does surveys of the coastline to help ships navigate for commerce and also military purposes in the United States and outlying regions. Another component of the agency that's fairly old, two components actually, is the Weather Service, which was founded in the Civil War era in the late 1800s. Of course, being able to do weather forecasting is very important for military operations, for commerce, and for safety. And so that was another very early activity that was founded separately and then brought into NOAA in 1970 when NOAA was created. And then the last component I'll mention is fisheries, managing our nation's fisheries, the different fish stocks that are caught and commercialized in the United States, and that also dates to around the Civil War period. So there are these kind of ancient, from an American perspective, components of NOAA that give us a lot of pride and claims on a long heritage of science in the agency. So I thought I would just give a little history there. In terms of where I'm located, NOAA has a number of functions, as you've already heard: coastal survey, weather prediction, managing the nation's fisheries. Now we manage a lot of satellites that observe weather and climate from various points in orbit around the Earth. We also predict and monitor the sun and issue solar forecasts, which are really important for protecting electronic equipment and activities, commercial activities that are reliant on or could be affected by solar flares and such. We have a National Ocean Service, which issues a lot of information to help individuals deal with storm surge and flooding, but also long-term sea level rise from climate change, and which also does a lot of coastal restoration when there are extreme events that can impact ecosystems and communities along our many thousands of miles of coastline. And we also have a research office at NOAA, and this is where I'm located. So we have this one office at NOAA that's really focused on advancing and exploring the research needs that the rest of the agency has. So we have a variety of different programs that help to advance our ability to predict weather, to understand climate, to prioritize satellite measurements that we need to take to help us understand change in fish stocks and be able to manage those fish stocks so that they're sustainable for a long period of time into the future. Understanding sea level rise and its effects in different parts of our coastal regions in the United States. So there's a lot of different components, and I'm focused on research that helps advance the climate mission at NOAA, which is distributed really across the entire agency, thinking about the effects of climate change on fish and ecosystems, on the coastlines, on our land and agriculture. So we work pretty broadly in my office in particular on advancing our understanding of climate across the agency and our ability to predict it and tell the public, inform the public of the type of changes that we're seeing currently and that we expect in the future. So hopefully that's a helpful overview of NOAA and situates me a little bit. I hope I didn't lose too many folks with that, because it is a complicated agency with a lot of different mission spaces. But as a person who gets to work across all those mission spaces, it's really a fascinating, dynamic place to work where there are so many different things that need to be done in the agency. It's very stimulating to work on a wide array of topics and issues.
Thank you for that, because I had realized that NOAA had done like the coastal charts, because I know I've used those products in my past life when I worked for the Department of Navy.
Cool.
But for some of the things that you talked about, I actually hadn't really thought too deeply about it. So it was really nice to hear kind of the history and the structure and how it evolved over time. But more specifically, I have two questions. One is, what kind of content does the Climate Program Office produce in terms of, I'm imagining when you make those predictions, there's some sort of a deliverable that you have associated with that. And then my other question is, how is NOAA working across those government agencies with maybe like Department of Defense or Department of Energy and things like that? But we'll maybe focus on the product question or deliverable question first.
Yeah. And you may enjoy this just on your point about the charts. A few years ago, the Office of Coast Survey moved to digital charts. So, they're a lot easier to access now. They used to be these huge posters that were printed out. And I think 7 or 8 years ago, this email went out in the building that I'm located in Silver Spring, Maryland, where they said, this is the day they're getting rid of all of their paper charts. They're moving to digital charts. Come on down and see, if you want to take these. And so there were just hundreds of people lined up in the hallway to go find, the chart of their favorite coastal vacation spot. For me, it's Cape Cod. Unfortunately, those were all gone by the time I got there. But some folks who, grew up in the Puget Sound were able to find charts of the local waters around where, they would go for vacation and whatnot. So that's a really cool thing. I do have a couple of those in the basement and need to hang them.
I have a couple of those too.
Oh, you do?
Cool.
Nice.
Yeah,
Maybe we can trade. So in terms of my office and content that's produced, I can kind of give two responses to that. The first of which is that our main function is not as a content producer, but a sort of research enterprise that supports the content producers. So as an example of this, the Climate Prediction Center, which is part of the Weather Service at NOAA, issues forecasts that go out up to 9 months in advance, generally of monthly quantities. So, right now they have forecasts of February 2024 average temperature and precipitation, and whether we expect that to be above, below, or near normal levels. And that's a very complicated type of forecast to make. There's a lot of uncertainty in that forecast. There are a lot of ways to make that forecast. There's a lot of information we can draw on, both from computer models that simulate forward how the climate and weather may evolve, but also using analogs from the past as well. So right now we're in an El Nino and headed towards a fairly strong one, which means that the sea surface temperatures in the tropical Eastern Pacific Ocean are much higher than normal, and that changes weather over the entire surface of the planet. And we can derive some knowledge from that, the fact that that's happening, and we know at some level predictably how the atmosphere responds to that change. And it tends to drive different patterns of temperature, precipitation, snowfall, things like that often, but don't always happen when there is an El Nino in the tropical Pacific. So there are a lot of different ways to go about making that forecast. And the forecast itself is issued by this office in the Weather Service. cpc.nsep.gov is where you would go to find that. However, there's a lot of research that needs to happen to think about the best methods to provide that forecast, and then how to improve those methods so that we are able to provide better and better and better quality forecasts over time that have lower uncertainty and are more useful for decision makers. So what my office would do in that case is fund research, both at NOAA and in the external community, at various universities, working with other federal agencies to try to improve the quality of those forecasts and their fidelity, or reduce the uncertainty of those forecasts. So we're not actually producing the forecasts in my office. What we are is a research organization that's trying to help advance the agency's ability to produce better and better and more useful forecasts. Other examples of this are improving our knowledge of and measurements of greenhouse gases in the atmosphere. We have programs in my office that are focused on that. Improving our computer models. My program focuses on that. We have programs that are trying to better understand, for example, to the example I gave of El Nino, how does El Nino affect the atmosphere globally? That's a very complicated question. How is climate change interacting with El Nino? That's a complicated question that we don't necessarily have clear answers to yet as a scientific community. So we're funding the research to try to advance our understanding of those questions, ultimately at NOAA, towards this goal, not just of creating knowledge and publishing papers, but of actually issuing better quality information to the public that's more reliable for decision making and planning. So that's kind of the one answer. The other answer I would give is we do have a really excellent team at my office, which runs the website climate.gov. Obviously, a very nice web domain to have, climate.gov. So it is the primary government website for climate information and reporting. They write news stories. There's data products that are available through that website. So there is content creation that comes out of my office as far as knowledge about climate change, trying to communicate it in a way that's understandable to a fairly broad public that has different levels of scientific understanding. And so I would encourage folks to look at that. There are a lot of fantastic articles there that help you better understand climate variability, climate change on long time scales. And that group is also helping to bring together some tools so folks can look at climate model data or climate observational data to get a better understanding of how climate is changing close to where they live. And also showing examples of how communities have adapted to climate change, because we can learn from those success or failure stories and apply them to other adaptation efforts in other communities. So that's kind of the content question. I can pause, but I can also answer your question about how we work with other agencies as well. But that was a lot, so let me pause for a minute and see if you wanted to follow up or pivot.
Well, yeah, I was just going to clarify. So mostly when you're working across agencies, it's with respect to improving the methods for the research in that respect. Is there certain agencies that you're mainly working with to do that, or are you mainly also working with, I'm imagining, universities and institutions that have a lot of research going on as well outside of the government? I'm just curious.
Yeah. So the example I gave with the Climate Prediction Center, the Climate Prediction Center is located in NOAA. So, primarily what the Climate Program Office and the other, like the Weather Program Office, the Ocean Program Office, their primary focus is on advancing our capabilities at NOAA. Our research is really grounded in attempting to advance our capabilities in the agency. But there are, first of all, a lot of stakeholders. There are a lot of other agencies that consume and use the climate predictions that come out of NOAA. The Department of Agriculture, for example, uses our rainfall, precipitation, and temperature forecasts to help its agricultural communities prepare for the growing season, managing their crops effectively through extreme events, things like that. There's a lot of collaboration between NOAA and the Department of Defense, which of course has a really critical interest in weather and climate prediction, and also climate change. A lot of Department of Defense facilities are highly exposed. Many, all of the naval facilities are along the coastlines, so they're very exposed to sea level rise. This is an issue, that the Naval Academy, for example, is dealing with in Annapolis, pretty close to us, in the Baltimore, DC area. So we work with a lot of the other agencies. In terms of driving the research, NOAA, of course, has an incredible set of researchers at our various laboratories around the country. We have laboratories in New Jersey and Miami and Seattle and Boulder and Norman, Oklahoma, all across the country. And these researchers, help to advance our ability to do prediction and make projections and create better models. But there's an even larger community outside of NOAA in the academic community, the academic sector in particular, but also the private sector that we work with as an agency to collaborate on research and bring these good ideas from the broader public into the agency to help advance our capabilities. And my office facilitates that through funding opportunities, grants to the external community, to try to engage those researchers with the NOAA mission and help us advance our agency's mission by collaborating with those communities.
Excellent. Thank you for clarifying that. I appreciate
Sure.
that. I'm going to pivot a little bit because I know in your bio we talked about you serving on the Federal Steering Committee for the NCA, or the National Climate Assessment. At the risk of using too many acronyms in a talk with someone who works for the government, can you tell me more about the National Climate Assessment?
Yeah, the acronym thing is so on point. I was actually talking to an early career colleague yesterday who was really proud that she had just created her first acronym, which is like a huge rite of passage for a government employee. So I'll try to just say the assessment, I guess, as the common reference point.
Okay.
So the National Climate Assessment is a really major product of the federal government pertaining to climate impacts. And fundamentally, it's a very long report. We're actually about to release the 5th version of this report, hopefully, in the next 2 to 4 weeks, actually, which is the culmination of years of activity going back to the Trump administration, actually, on this assessment. So we've been working on it for multiple years now. It's a huge effort. Over 2,000 pages, 500 authors, 30 chapters. It's an enormous undertaking. And it's really a cornerstone product of the federal government to try to assess what we as a broad community in the federal government and outside of the federal government perceive to be the things that we know about the climate system in the United States and relevant to United States concerns, and how that system is changing over time and how we expect it to change in the future. So the word assessment is really a key word because it actually points to a process of bringing groups of people together with different expertise and different points of view on what we know and understand to try to come to some sort of consensus on the state of knowledge and how confident we are in that state of knowledge today, or at least in this time period, a couple years around the release of the report. And so it's really kind of a convening. It's a discussion. It's a review of knowledge and data and published literature to try to come to a best estimate of our confidence regarding the climate system and how it's changing and how it's going to affect our economy and people. So the report is led by 14 different federal agencies. NOAA is one of them, NASA, Department of State, Department of Interior, Department of Energy, Department of Defense, all of these players that have some degree of engagement with the concept of climate change in their mission. They're involved with this report and help guide it. And the process it's a very transparent, open process. So we have a number of points along the way where we seek public input. We had meetings that were open to the public back at the beginning of the cycle. We asked for the public to suggest authors, to provide input, to tell us what they thought about the chapters that we proposed. And then the public also had a lengthy opportunity to review all of the content that was then written by the authors and provide feedback. And we hold ourselves to a very high level of accountability. Every single one of the 3,500 comments that we received from the public had to be specifically read, considered, and either responded to with a message back to the commenter, or an edit had to be made to the chapter to correspond with that comment, to address that comment if the comment was valid, if there was a valid basis for what that comment said. So being an author on the assessment, you don't get paid for it. It's totally a volunteer effort. It's a lot of work, but it's a really essential product, and it's done in this really kind of open manner. The other thing about it is that when it's released, I encourage folks to take a look at it, and you'll see, I'm sure there will be front page headlines when it's released, on what the findings are. But go take a look at it, because the other thing is that we try to be really clear about how we get to the conclusions in the assessment. So there are these major conclusions that appear very prominently in each of the chapters. And if you click on them, you can actually go to what's called a traceable account, where it'll explain how the authors got to that conclusion. And there's usually 3 pages of text for 1 paragraph of a major top line conclusion to articulate, like, here's what we considered. Here are some of the things that gave us pause in terms of confidence in the statement that we made, or some of the evidence that gave us a lot of confidence in the statement. So it's a process. It's not just a bunch of people just going and saying what they think and dumping that on a website. There's a very long process of engagement with the public and trying to bring a lot of people into the process, and then trying to explain how what our evidentiary basis was to come to certain conclusions in the report. So it's coming out, hopefully very soon, and we're working through, how we're going to engage on the report with the public. The White House is interested. We're planning to have webinars and a rollout event and things like that. It's just the timing of it is not totally set in stone at this point, but we're very excited to get it out. And we've already started thinking about the next assessment because we're required by law to produce this assessment every 4 years.
Wow.
So yeah, it's a lot to write a 2,200 page report every 4 years. So we're already starting to think about the NCA 6 process a little bit now too. Is that kind of the information you were hoping?
I mean, I'm amazed by the process that goes on behind that. I posted a link to the NCA 4 since NCA 5 is not yet out. But so let me get that straight in terms of timeline. When they come out with the assessment number 5, is there a period of time in which they're then engaging with the public, getting comments and addressing all those comments, and then they tweak it before they release the finalized version? Or is it in that stage right now? Or is that part of the 4 years?
So there are basically 6, for this assessment, there were 6 major drafts of the assessment. The first draft that was approaching 2,000 pages with kind of all of the content filled in, that's the draft that was sent out to the public, because we felt at that point, this is really like a full product from the authors. They're done at this point from their perspective. Okay. And now we're going to go through this iterative review process. So it's really the third draft that received the heavy public scrutiny. After that point, the changes are really just supposed to be in response to the public comments, and then in response to any further concerns or comments from the various agencies that are responsible for producing the report. So the change from draft 0 to 3 was enormous. Like, the whole report was created. Draft 0 is the table of contents. The changes from draft 3 to draft 6, which is the draft that will be released as the final version, are much smaller. The content should be very similar to the version that was released to the public, except for changes that were made in response to public comments, to agency comments. And the other thing is also the report receives a review from the National Academies of Science, which is sort of an independent group that provides scientific advice to the federal government. They gave us a 350-page review of the report, so we had to also work through that as well to integrate some of their comments.
Okay. At least it's shorter than the actual report. Okay, right. Well, that's amazing to hear about the process. I appreciate that, and it's nice to hear about the level of engagement with the public as well. While I have you, I wanted to ask a question that I know that you get often, and I know I get in my own classes whenever I'm talking about climate change. So, and I know we talked about discussing this when we were together. I'm going to let the expert answer it. How do we predict the climate, which is even more long-term than weather, if we can't predict the weather beyond a day or two? I hear this question often, and I know you do. So I'm curious, how do you answer that when you get it?
Yeah. So it really depends on the time lead that you're trying to make a prediction of. So, for example, if I'm trying to predict 10 minutes from now, the weather outside is going to be very similar to the weather right now. Tomorrow, probably similar, unless there's a major storm system coming through. A week from now, probably also fairly similar, again, save for weather systems. Right now, we can make pretty good predictions of short-term weather, so a few days in advance. Actually, I don't have the exact figure on my mind at the moment, but I know I always want to try to defend meteorologists who are the butt of so many jokes and hatred. Weather forecasts actually are getting better. Believe me. I hope you believe me. I'm close to the activity, so I hope you trust my perspective on this. But they are actually getting better over time. So right now, a 4.5 or 5 day forecast is about as good as a 2-day forecast was back in 1990. So we've gained about 3 days of useful skill or quality in our weather forecasts, just from improving our models, improving our understanding, improving our satellite technologies and the observations we get from those satellites, and various other activities associated with the forecast enterprise. So we actually have a pretty good ability now to predict daily weather out to sometimes as long as 10 days into the future. But then once you get beyond 10 days, there's so much chaos in the atmosphere system, in particular, fast chaos, that your ability to make a prediction falls off dramatically after about 10 days, after about a week and a half, when you're approaching that 2-week kind of boundary.
Can I pause you for a second?
Yeah, absolutely, please.
What is fast chaos?
So the atmosphere is a fairly fast system compared to, say, the oceans, where they evolve. The oceans evolve more slowly than the atmosphere does. So the rate of motion of the atmospheric fluid is much higher than the rate of motion of the ocean fluid, of water. Currents versus winds, basically.
Okay.
And so if you think about, if you have an uncertainty today in the atmospheric system, that uncertainty can grow much faster in the atmospheric system than it can grow in the ocean system or in the land system, in trying to predict forward, what the condition in that system is going to be. My favorite way to just think about chaos is, aside from the infamous Jeff Goldblum scene in Jurassic Park with the flirtatious drop of water on the hand, is thinking about bowling, which I think we've all probably done at some point, and the fact that it's very hard to throw a strike. It doesn't seem like, just if you step back, it doesn't seem that complicated. You're rolling a ball down a lane, it's flat. You can do this many, many, many times. And even if you practice, like most of us cannot, throw 10 strikes in a row. It's very difficult to do. And the reason for that is because even if you try to duplicate perfectly as you as a human system can, the same approach, the same release point, the same velocity on the ball, the same spin on the ball, the same angle that the ball takes down the lane, there are, first of all, small, uncontrollable differences in our bodies and our ability to release that ball in exactly the same way. There are small imperfections in the ball, in the bowling alley surface. And those imperfections lead to small changes in the beginning that, as the ball rolls down the lane, become larger and larger and larger over time, until you get these very large deviations at the end of the lane that results in a very different outcome in knocking the pins down. And not to mention, the pins are not being placed at a microscopic level at exactly the same positions each time. There's some small amount of variability there. So it's very, very hard to control all of those factors that make bowling fun, that allow that small amount of differential to grow into a large enough differential that you get a gutter ball, or you get the ball only hits one pin on the side, right? So it's kind of the same thing in the atmosphere. A very, very small change can over time grow into a much larger, different outcome in the future. And so the end of the bowling lane is kind of like a 10-day forecast, where over that 10 days, over that length of the bowling lane, that outcome can change quite a bit as that chaos and an initial kind of problem in the system can grow over time. When we're trying to make longer forecasts, we're not trying to predict what's going to happen on a given day. So the nature of the problem changes. We're no longer in this paradigm where I'm going to try to tell you, Jen, what the forecast is going to be on Halloween, so we have a sense of like whether my kids are going to be wearing a jacket under their, we're going to try to stuff a jacket under their Halloween costume or not. We're not trying to predict that when we're looking 2 months, 3 months into the future. We're just trying to predict that month. And so we're no longer running a weather model. We're now running a climate model. We're now looking at El Nino. And what do we know about El Nino in November or December of an El Nino year? What type of patterns does that tend to provide us? And we get information from that. When we go much longer into the future, so looking decades into the future, where the main driver of change is climate change, we're often looking at an annual average, just an entire year. And the condition in that year, let's say 2060, is going to primarily be governed. So for a year, not a day within that year, but the entire year is going to be governed by the amount of energy in our atmosphere and ocean and the boundaries on that energy. And the boundaries at that time scale are determined by the state of the sun, the state of the volcanic systems on Earth, and most importantly, the amount of greenhouse gases and aerosols that are in the atmosphere. And so we have these scenarios and projections of what we expect in terms of emissions over the next few decades. And we can use those and provide that to a climate model to say, this is kind of what the energy situation is going to look like in the atmosphere, the oceans, and the land. What kind of weather do you think we're going to have in that scenario a number of decades into the future? How is the atmosphere going to behave in that future? Is it going to be similar to today, or is it going to be different because it's being given this much larger amount of energy to work with that can change storm systems, variability, thermal impacts, things like drought, all of these different phenomena that we're concerned with. So it's just a very, I guess my short answer is, looking at climate change and trying to project decades in the future is just an entirely different information problem than trying to predict next week's weather.
Yeah, that makes sense, because essentially you're saying that by using averages, which we're doing when we use climate data, we can go further into the future, and we're not trying to figure out what's happening on that day, but more like what's happening in that month or what's happening in that year. I'm trying to, for the sake of people listening in who maybe aren't from a climatology background, think of what would be the analogy if bowling is to weather prediction. What would be the climate analogy? I don't know what that is. Maybe you have a better analogy.
Yeah, so it's like putting bumpers on the bowling lane, right? If you remember going to a kid's birthday party, they would put those inflatable bumpers. Okay, so so maybe like Jen 2023 birthday party still using the bumpers. So, but that's what the climate problem becomes, is we have these boundaries then on the problem that kind of limit the number of outcomes, right? In that case, you put the bumpers on the bowling lane, you know that you're going to knock down, hopefully you knock down a pin in that case. Otherwise, there's something skillfully really off there.
I usually do.
Right. And so the boundaries in the case of climate change are the greenhouse gas forcing. That's giving us a sense of what the boundaries are going to be on possible future outcomes. So we know if we're adding more greenhouse gases to the atmosphere, we know that greenhouse gases help the atmosphere absorb heat, which it can't get rid of quickly enough. And, from like a 100-year timescale perspective, and that heat is going to change many different aspects of how the atmosphere and oceans and land surface function, and the type of weather and the type of climate events that we get. And so it's kind of those boundaries that you're guiding then the solution within boundaries. You kind of know what the upper and lower boundaries are at that point based on our expectations of emissions, and also committed change now just from the emissions that have already happened.
Okay.
Is that helpful?
I appreciate that. Yeah, that's very helpful, I think, for giving someone a visual, and it maybe even extending that and saying, well, maybe you won't know which pins are knocked down, but you might have an idea of the proportion that would be knocked down. I don't know, exactly, in terms of like averages. So yeah, I think that provides a nice visual for people that are still trying to differentiate between weather and climate, because there's a lot of confusion out there, I think, between weather and climate that I seem to hear about every day. I appreciate that.
Sure.
I wanted to turn more specifically, because I know you've done a lot of research with respect to droughts and thermal events. And well, I guess first of all, can you tell us, and I guess we a lot of us have kind of a view of how these are changing with respect to climate change, but in your expert opinion, how are these changing due to climate change?
Yeah, so thermal events like extreme temperatures, heat waves, and also cold snaps or cold waves. Those are a little bit simpler to understand in the context of climate change, where in general the direction we're going is towards a warmer planet with more energy in the atmosphere. And so we're kind of lifting all events in that respect, because the average temperatures everywhere are increasing. Everywhere, there are some exceptions to that, like the central and southeast United States is one place where there hasn't been as strong of a temperature trend over time. and also the North Atlantic because of a slowdown in some of the ocean circulation there. But pretty much everywhere else, temperatures are just monotonically increasing over time. And so, a heat wave from 30 years ago is now going to be, on average, somewhat hotter because you're lifting the baseline level of that just from raising the average temperature at a regional and global scale. So those are like a little bit simpler to think about at that level. But a heat wave is fundamentally usually associated with some type of a weather system, where in the United States, what you're getting is a large ridge basically in the atmosphere where there's a lot of air being moved up north from southern regions. And so you're getting this unusually warm air moved into a region where that air is not, the thermal characteristics of that air are not commonly that warm. And then you may have some local effects that can amplify that. Like, for example, if there is a drought in a region, and then there's a ridge that draws warm air up over that drought region, that can amplify the heat wave because there's less of an ability for the atmosphere to cool itself down via evaporation from the ground and the energy that can be absorbed by water in that case. And so you can amplify the heat wave in the situation where there's a drought prevalent there. So, the simple answer to this is that the frequency in the United States, especially the frequency and the length of the season during which heat waves happen, are both increasing over time. We're getting, in parts of the Southeast United States, for example, the heat wave season, the season in which you would expect to see a strong, say, 5-day period with extremely high temperatures, has gotten 60 days longer over the last few decades. So you have almost 2 more months now, both in the spring and in the fall, where you're seeing the possibility of heat waves existing when they wouldn't have existed in that part of during that part of the calendar in parts of the country. The other thing is that the intensity of the heat waves is generally going up pretty much everywhere in the United States. I was going to add one thing to that, but it's kind of slipping my mind at the moment. But on the drought side, drought compared to heat waves, it's a very different phenomenon. First of all, a heat wave is usually a few days where the temperatures have elevated. A drought is usually a period of a number of months or even a number of years where it's very dry. And drought is the drought research community can make drought very complicated. There are hundreds of different ways to describe drought because it is a complicated phenomenon. But basically, it's where there's a lack of water to meet the various demands for water in a particular place. And demand can take a number of forms. So obviously, the thing we think about first is turning your faucet on. The human demand for water. Like in the southwestern United States, we have a problem right now where there's a lot of human demand for water that's not consistently being met by the amount of water that's generally available in the southwest United States, but especially now is decreasingly available due to climate change, but also some natural variability patterns over the last 20 years. Another major demand for water is the atmosphere. So it's a natural demand. The atmosphere generally in drier places removes a lot of water from the land surface. So in California and the southwest United States, the atmosphere is generally sucking an enormous amount of water out of the land surface and is a huge piece of that demand. So demand can take a number of different forms, both human and natural in that respect. And so if you get a situation where you don't get as much rainfall as you expect, and where demand, both from the atmosphere and humans, is higher than what can be supplied based on the precipitation, the reservoirs and rivers, and then the subsurface water, the groundwater, then you get into a situation where you have drought, where there's just an absence of the amount of moisture that the environment and the people in that environment need to sustain life, to have a healthy ecosystem, et cetera. And so because drought is complicated, its relationship with climate change is also quite complicated. One thing that's really clear, though, is that because the atmosphere is warming up, the one definitive thing that we see is that atmospheric demand for water is going up. And that has especially been problematic in the southwest United States, which is getting so much hotter than it used to be 30, 40 years ago even. You had records in Phoenix this summer, an unprecedented number of days in which the air temperature got over 110 degrees Fahrenheit. The higher the temperature is, the more evaporation is happening, and the atmosphere is stealing that water from people and the land surface. And in general, in the southwestern United States, we've been in a 20-year natural period. Generally, the scientific consensus is that we've had a natural drought the last 20 years that now has climate change on top of it. So first of all, that evaporation has increased, but then second of all, it's also possible that climate change has been affecting where storm systems are landing on the West Coast and driving them away from the southwestern United States. So we're also getting less precipitation. We are also getting less snowfall. And the problem with that is snowfall, in high parts of Arizona, in New Mexico, Colorado, Utah, that snow, it falls, it generally lasts well into the spring so that it provides this continuous trickle of water into the rivers and streams and ground well into the summer. If, first of all, that snow is melting earlier in the year, it means that there's less available water in the summer when we really need it in the Southwest to grow crops, to keep people cool, for potable water consumption. But also less precipitation is falling as snow too. We're getting more rain, which runs off much faster. So, there are a variety of ways in which climate change can have fingerprints. It's not entirely responsible for what's going on in the Southwest right now. There's land development, there's some natural variability, but it is a big piece of the puzzle to what's going on. And that's kind of climate change in general. It has changed everything. The fingerprints of climate change on a particular event is a very complex question that in some cases there's a large climate change effect. In some cases, it might be a much smaller effect on a particular event, and it depends on the nature of the event.
Thank you for explaining that. I appreciate that. And I want to go back to, you mentioned ocean currents earlier, and I know that there's been some research that came out this year and a few years earlier about how the ocean isn't changing in response to climate change. And in particular, there's been discussion about Atlantic, the thermohaline circulation, the deep ocean currents slowing down. To what extent should we be concerned about this? I guess is my question. And what are your thoughts on some of this research that's been coming out?
Yeah. So the thermohaline circulation is a really key phenomena. It happens to occur in the North Atlantic, so it's pretty close to home for us, right off the coast, and then the northeast coast, and then near Iceland and the southern portion of Greenland is where a lot of the action is happening for that current. And it's different. I'll just mention it's different from the currents we think of, like the Gulf Stream current, for example. The Gulf Stream is driven by wind, but the thermohaline circulation is driven by much slower density differences in the ocean. So the water in the North Atlantic is very heavy, first of all, because there's a lot of evaporation from wind. And so that takes water out of the surface ocean, which leaves a lot of salt behind, which makes the water dense and more prone to sinking. But then also the winds tend to extract heat from the surface ocean in the North Atlantic, which makes the water colder and more dense and also inclined to sink. So that's where that name comes from: thermo, like temperature, thermal, and haline, which is like halides or salts. So it's a compound term that refers to the temperature and salt characteristics, salinity characteristics. And it's a very abstract phenomena, I think, but it's really key to the global climate because it's one of the ways in which the oceans are taking in an enormous amount of heat from the atmosphere and burying it deep in deeper layers of the ocean. It also drives, especially climate in the North American and Western European or Eurasian regions, because it's transporting so much heat throughout the ocean system and exchanging that back and forth with the atmosphere, that if this phenomena shut down, it would vastly change the climate of Western Europe and North America as well. This is like the Day After Tomorrow was kind of
movie.
Like that idea of creating this insane sort of version of it. But it's a really critical phenomena. It has shut down before and has changed regional weather conditions by a significant amount. And there was, yeah, as you mentioned, there was that study that came out a few months ago, and there were a lot of headlines on it and a lot of kind of panic over it. It's a very critical phenomenon for sure. Our climate in North America and Europe would change significantly without it, and if it shut down. It is slowing down, but generally the consensus is that it's not slowing down or expected to slow down as much as that single study anticipated.
Okay.
But I think that that study sort of points to the process of science where, we have a general understanding and consensus now. That paper is a new contribution to that will be considered with the other evidence that we have. And it's a piece of evidence. It doesn't mean that paper is wrong just because it's a little bit different from where the consensus is. This is a really good example of how science works, is people publish these kind of findings and it sort of gets filtered through the community and understood in the context of where we've come from with our understanding and what the other evidence shows as well. That particular study, I would say, is kind of on the edge of like a very aggressive scenario compared to like where the consensus position is in the scientific community. But directionally, it's very much in agreement that the AMOC is probably already showing signs of having slowed down. We don't have a ton of good observations of it for a long term. It's a very hard phenomenon to observe well. But there's some evidence that it has slowed down already, and most climate models expect that it will continue to slow down by a pretty decent amount over the next few decades out to the end of the century under a whole array of different climate scenarios and different emission scenarios.
That's interesting to hear.
Don't be terrified about it.
Yeah.
It's not science fiction. It's not the day after tomorrow, but it is a really important phenomenon, and it is changing, and it's changing because of greenhouse gas forcing. The extent to which it completely shuts down, which would be very significant, versus slows down and maybe alters some regional climate conditions, which will still have significant effects and manifest significant effects. That's kind of the question. And I think that that paper was really envisioning the possibility that it could stop, which would be a very serious tipping point for our climate.
Yeah. So it's really making a good case for consistent monitoring and prediction of all of these different systems to make sure that we have accuracy moving forward, and scientists can keep doing what they're doing in terms of studying what's happening and making more accurate predictions moving forward. For the sake of time, I want to remind everyone listening in that you can post questions for Dr. Barrie in the chat. I wanted to ask one more question. I know I had a lot for you, but I'll ask one more question, and then while people are typing. What led you to your career in climate science?
So there's a term of endearment in the weather community, in the meteorologist community, called a weather weenie, which is like a person who is sort of unduly or excessively interested in the weather. And I am definitely like a certified weather weenie, going way back to being a kid growing up in upstate New York. I grew up in Albany, New York. And for me in particular, like my interest in the atmosphere relates back to an intense amount of excitement over the possibility of snow days as a kid, and being outside with my friends, not having to go to school. Albany, when I was a kid, did get a lot of snowfall. We had a couple of instances where school was actually closed for an entire week. And this is in a pretty hardy place that has a large snow removal budget. It just wasn't possible to get your car out of the driveway or, navigate around the city and get to school. So school was closed for multiple days a number of times when I was a kid. And I was, I loved going outside and being in the snow and building snow structures and having snowball fights in my neighborhood and all that kind of stuff. And so I was just hugely into weather, I think particularly winter weather for that reason. But then also, like, I'm kind of artistically inclined and I love looking at the sky. I just think the sky is this extraordinary, equitably accessible, beautiful feature of the earth. Just looking up and looking at clouds during the summer and seeing thunder clouds develop, it's just endlessly stimulating for me. So I'm just a big weather weenie going back. When Twister came out, the movie Twister, when I was a child, that just kind of like totally did it. That was too much for me. And so I ended up, when I was in college, I studied physics, and atmospheric science, climate science, is really just a lot of physics and chemistry and then computing science and biology. It's kind of a nice meld. And so I really liked the idea that a nice way to apply physics and chemistry, which I also love, in a practical sense was through studying the atmosphere, studying the ocean, and kind of working in that space. So that's really my origin story. I remember I would watch the Weather Channel constantly. Anybody who's watched the Weather Channel or like is on Twitter, the meteorologist Jim Cantori is like notorious for showing up in storms. He came to Albany for a number of winter storms when I was a kid, and I remember it was like I was like, oh my God, he's down, by the state capitol and whatnot. So that's my origin story. I've just always loved the weather, and now climate is a topic that's evolved a lot. While I was in grad school, it really gained a lot of momentum, and it's just an incredibly important societal topic where we really need good information and good science to help us make good decisions going into the future. So, it's a field that also now I feel a lot of sort of like moral passion around, and it's wonderful to be involved in the climate field.
I appreciate your background story, and I think a lot of people I've talked to go into certain sciences because of usually a childhood passion. So I can definitely relate to that. In the geosciences, we're called rock lickers, not. So we have a similar weird name.
Oh, that's great.
We do have one question from Ben. Ben asked actually earlier on in our conversation, do you find that lots of people from the general public come directly to NOAA for information about climate change, or are they usually going to other places for information?
Yeah, great question. So and I think this actually points to a bit of a problem that we're trying to solve as an agency. So the answer is yes, we get so many requests for information. And sometimes, and we don't have a facility to engage those questions currently. If you have questions about weather, we have a whole facility for that. You have a local forecast office likely within 20 miles of where you live. You could call them up or send them an email and you will hear back or reach somebody today if you have a question about the weather. People often call those meteorologists as well with climate questions, but they're not really trained in that. It's not their job to be answering questions about climate change. And we're kind of lacking in this facility at NOAA to be able to answer the mail for climate in the way that we do for weather. And that's actually something I've been really integrally involved in at NOAA over the past 2 years, is developing a service where consumers can ask our agency specific questions. Right now, we're working with the American Society of Civil Engineers, which issues all of the planning and guidance documents to local organizations that set engineering standards, because they're really interested in better understanding how precipitation and temperature and winds are expected to change around the country in the future. And that obviously has direct implications for the type of engineering decisions we should be making so that our structures are more resilient to those potential changes. One change I'll mention really quickly is that hurricanes now are strengthening much faster as they approach landfall, and they're also maintaining their strength farther inland. So that really changes the considerations, even in a place like Baltimore, where we're 150 miles from the coastline. The wind speeds of a Category 4 or 3 hurricane making landfall in Delaware that can reach inland now to Baltimore, much higher than they were before. So we have to be changing, this information and providing it to groups like ASCE. But the answer to his question is yes, and I really appreciate it because it's motivating a lot of work that I'm involved in and my colleagues are involved in to try to improve this.
Excellent. And I think we may have 2 minutes left for Valerie's question. And this is a good one too. Are we at the point now where we may be considering using AI, artificial intelligence, to enhance predictive models and suggest mitigation methods?
Yeah, AI has a lot of promise. It has a lot of limitations as well in trying to do prediction, because prediction is a very complicated phenomena that's not always analogous to like doing image or just data analysis. There's also a lot of physical intuition, and we know that the AI models are kind of lacking in that when you look at like a large language model, and it sometimes produces good answers, but then other times when it gets out of its comfort zone, it's very confused. It's kind of the same thing with a lot of data AI models as well, where if you're thinking about a very, very unexpected, rare, extreme event that's kind of out of the historical sample, AI models, which are based on the historical sample, are going to really struggle with producing an event that's not in that historical example. So like the Ellicott City floods, for example, or the Pacific Northwest heat wave. Those are things that are going to be challenging. But we are using AI approaches for a lot of different things, including making weather forecasts, starting to think about applying them to climate forecasts, using AI tools to help analyze the massive amounts of data that are coming out of our models that are very, very hard to analyze with traditional statistical methods. And there's a lot of work to use AI approaches to improve our models, to improve parameters in the models, to help make model output at higher resolution. There are so many different really effective applications of AI. And we're doing it at NOAA, where we're working with the private sector to do it. And we're also working with the academic community to try to experiment with some of these approaches, because it is very promising in a number of different use cases.
Oh, it's exciting to hear.
Question. Yeah.
Yeah, well, thank you. And I know we're right up at 1 o'clock, so we don't have time for any more questions, but I want to thank you, Dan, for the wonderful conversation about climate change and predicting climate. And I want to thank our audience members for joining us as well. I will be sending out the link to the recording probably by tomorrow. And then I also want to do a shout out to Taylor, who's been working in the background. She's our graduate admissions counselor who's helping us run our events here. And she's sort of like the Wizard of Oz. She's behind our curtain and she's letting everyone in. So if you have time, please thank our speaker in the chat, and have a wonderful rest of your day, everyone. I appreciate you joining us.